Hi everyone, I'd like to work through an application of the product and quotient rules. The camera intensity problem was an application of the quotient rule, but I have another nice one here that I'd like to look at. Okay, so first the product rule. So these kind of come in two different types. One is this more general type where you're just given some information about values of something and how fast it's changing, and you're asked to picture on your own how a product or quotient rule applies. So here, we have day 10 of a large construction project, and we know that there are 28 workers on the job, and 3 workers are expected to be added. The average workday is 10 hours, so each person works 10 hours on average, but this is expected to decrease by half an hour. We are supposed to find the instantaneous rate of change in the total number of man hours per day on day 10. Man hours. I love product units. They're like my favorite thing. Foot-pounds, man hours. We see them more in calc too. So first we need to think about this. We're looking for the instantaneous rate of change in number of man hours. Okay, so number of man hours is basically if you take all the hours worked by all the people, that's the number of man hours. So it's something that we have to figure out how to calculate from the information we have. So this is going to be, I'm going to give it a variable name. So let's say M is, and we'll do M of T, is the number of man hours on day T. So this is a function of time. It would change depending on which day. And then if we want to figure out how to find the total number of man hours, if we look at the information we're given, we have number of workers and we have average length of workday. So let's say W of T is the number of workers on the job, and again this would be on day T, and then H of T is the number of hours per worker on day T. Okay, so we have all of this stuff. If we want the number of man hours, we need to multiply the number of workers by the number of hours per worker. And units should help you. If you're ever stuck on this, if you look at this, if we want a total number of hours, we need to multiply the number of workers by the number of hours per worker. So we'll say M of T is the number of workers multiplied by the hours per worker. Okay, so we wanted the instantaneous rate of change in the number of man hours. So we're looking for an M prime of T. And this is a product, so it's going to be a product rule. We'll get an H times W prime plus a W times H prime. So that's how we would calculate the instantaneous rate of change in this thing. So if we want M prime of 10, we would say, okay, H of 10, that should be the number of hours per worker on day 10, and that was actually 10 hours per worker, 10 hour days. And then this W prime is how fast the number of workers is changing. So we said that it was expected to have 3 workers added. And then we need the number of workers, 28, multiplied by the rate of change in the hours. That was expected to decrease by 1/2, so that's a negative 1/2. So we end up with 30 minus 14, which is 16. And then the units are hours per day, or man hours per day if you want. So right on day 10, the total number of man hours is increasing by 16 hours per day. Okay, so there's one that's a little bit more abstract. And then the other thing you'll see, which I hope doesn't give you too much trouble, is sometimes you're just given a formula and asked to figure some things out and interpret. And in that case, you'll just need to apply product or quotient rule to take derivatives. So in this one, we have a function C of t that gives the concentration of the drug in milligrams per cubic centimeter. That's for C. T hours after an injection is given. So a patient has a drug injected into their bloodstream. The concentration of the drug in the bloodstream is given by this function C of t. So we're supposed to find C prime of 3 and C double prime of 3 and explain their meanings. So let's first find C prime. C is definitely a quotient, so we're going to take our bottom, t squared plus 1, and we're going to multiply by the derivative of the top, which will just be a 0.14. And then we have a minus the top, 0.14t, times the derivative of the bottom, which is 2t. And that's divided by t squared plus 1 squared. Okay, so I am going to simplify, but it's not to plug in the 3. It's because I need to take a second derivative, and I want this thing to be as simple as possible before I go doing that. So I'm going to say C prime of t. I'm just going to multiply out and see if anything nice happens. I have a 0.14t squared plus 0.14 when I distribute. And then I have a minus 0.28t squared. So a little bit of nice stuff happens. I can combine 0.14t squared and negative 0.28t squared, and I end up with the 0.14 minus a 0.14t squared. Okay, so there's my derivative function. So if I want to find C prime of 3, I'm going to go ahead and plug it in and say I have 0.14 minus 0.14 times 9 over, I forgot what I was doing, plugging into 3, 9 plus 1 over 10. Okay, so negative 8.14. Okay, so phone calculator. Okay. We have 0.14 minus 0.14 times 9, and that's going to be divided by 10. So C prime of 3 is negative 0.112. Okay. I'm going to do interpretations when I have both of them. So there's the numerical value. If I want to find the second derivative, because the first derivative is still a quotient, I'll use another quotient rule. Oh, hold on, I lost a squared. Let me possibly change my mind here. Oh, here, that's actually easy. We just have to move our decimal place over 1. Okay, so we're actually dividing by 100. So now, when I go to simplify, I get a t squared plus 1 squared, the bottom, times the derivative of the top. So part of that's easy. Derivative of 0.14 is 0. And then we'll have a negative, bring the 2 down in front, 0.218. And then I want minus the top, 0.14 minus 0.14t squared, times the derivative of the bottom, which I'm not actually loving. So let's see here. The bottom, we'll just do a little side note, needs to be FOILed out before I can take the derivative, or you could use a product rule, but that sounds terrible to me. So we're going to get a t to the 4th plus 2t squared plus 1. So the derivative of the bottom is a 4t cubed plus 4t. And then that's all over t squared plus 1 squared, and then squared again is going to be to the 4th. Okay, so that's a horrible mess, but I don't have to try and simplify that. I just have to try to plug a 3 into that. So if I want, here, we'll put it right here, C double prime of 3, let's see if I can keep track of all this. I have a 9, 10 squared, so I have a 100 times negative 0.28 times 3 minus a 0.14 minus 0.14 times 9. I'm going to run out of room here. We're going to do a little bit of scratch work. 0.14 minus 0.14 times 9, which is negative 1.12. So this will become a plus 1.12. And then a 4 times, what am I plugging in? 3. 4 times 27 plus a 4 times 3, which is a 120. And that's all divided by 10 to the 4th. Okay, so there's my fraction, and let's go ahead and do it. So we have 100 times negative 0.28 times 3 plus 1.12 times 120 divided by 10 to the 4th. Hopefully I got all that in right. So C double prime of 3 is about 0.005. Okay. So in terms of interpretation, the original function, this was time in hours since the injection. And this was the concentration of the drug in milligrams per cubic centimeter, cc. Okay. So the C prime of 3 should have units milligrams per cc per hour. So that's telling me that at hour 3, 3 hours since the injection, the concentration is decreasing at a rate of about 0.01 milligrams per cc per hour. So over the next hour, between 3 hours and 4 hours from injection, we expect the concentration to decrease by about 1/100th of a milligram per cubic centimeter of blood. The second derivative is going to be milligrams per cubic centimeter per hour. So this is telling me how fast the rate of change is changing. So we're expecting the concentration to decrease, but this is saying that it's decreasing at an increasing rate. So we expect this to go up by about 0.005. So at hour 4, instead of expecting a drop of 0.11 milligrams per cc, we'll expect a drop of, we're adding, so negative 0.011, and we're adding 0.00, am I lining this up right in my head? 5, yeah, so we would expect it to drop, but only by negative 0.006. So you can add this on here, and that'll give you your estimate. So it's decreasing, but it's slowing down, decreasing at an increasing rate. All right, thanks for watching.